In this video, we're going to discuss using slicing and definite integrals in order to calculate the area of a triangle. So I've got a triangle here with a base of 12 and a height of 10. Now we already know the area of this. 1/2 base times height would give us 60, so we already know the answer. The point of this video is to introduce the idea of slicing and see where it can, and eventually we'll see where it can take us. So the way slicing works is I want to break this up into a whole bunch of rectangles. Now I have two options for rectangles. I could do vertical rectangles, or I could do horizontal rectangles. And either should give me the correct answer. But what I want to notice about this triangle is notice that if I do vertical, they're going to increase for a while and then they're going to decrease. So what the top of my triangle is changes whether I'm on the left half or the right half. So that tells me if I do this, I might have to break it up into two different integrals. So instead, I'm going to go with the horizontal slice because I see as I go down, what's going to happen is it's just going to continually get wider. Alright, so what we call this guy is the ith slice. What that means is it's the general slice for our triangle here. And so my goal is going to be, first, find the area of just the ith slice. Well, here's the idea. The idea is I've picked the ith slice so small that I can assume that this side and this side are straight, as opposed to the angle, the incline that we see, or decline over here. The reason that we do that is I want this to be a rectangle. So when I go to do the area of the ith slice, it's just a rectangle that's going to be whatever its base is times its height. Now, if you remember back from Riemann sums, what we would do is we'd pick all those rectangles to have the same width. So I'm going to do the same thing here. I'm only doing one slice, but what you want to imagine is this thing is going to be slice, slice, so on and so forth. So we're breaking it up the same way we did the curve. All the slices have the same height. I'm going to call it delta H. Now, I need to introduce a variable for this, because what you should notice is depending on which slice I pick, this value will be different. If that's the case, then you need a variable. If those are all going to be the same, you don't. So maybe I call it the base of the ith slice. So I like using that subscript to say I'm looking in my discrete case. So the area of the ith slice then is the base of the ith slice times delta H. That's all well and good. But what you want to notice at this point is I've got two variables going on here, H and B. We don't want to have two variables going on because this is only single variable calculus. So what I need to do is see if I can come up with a relationship between B and H that will help me figure this out. Well, I'm going to go back to my drawing and I'm going to notice something. Now I'm going to redraw it, not to the same size. I know my big triangle here is 12 and this is 10, and then I've put in my slice here and I've called this B sub I, and that means this is H sub I, the height of the ith slice. So this is miniaturizing my triangle here, just taking out some of the extra notation we have. Well, what I have between my big triangle and my little triangle are similar triangles. That means the ratio of their sides must be equal. So one option there is I could say H is to B, H sub I is to B sub I, as the height of the big triangle is to the base of the big triangle. 10 is to 12. Now what did I need? I needed something for B sub I in terms of H sub I. So I'm going to cross multiply here to get rid of my denominators. So I have 12 H sub I equals 10 B sub I, and divide both sides by 10. Of course, you guys can probably start doing this in one step, and that's fine. And this will reduce down to 6/5, so I get b sub I is equal to 6/5 h sub I. That's always true in this triangle. What that's going to allow me to do is rewrite this. Instead of b sub I, I'm going to put in the 6/5 h sub I delta h. What we have there is the area of the ith slice. Think about what we would do in the past. The next thing we would do is do our Riemann sum, and we'd add up the area of those ith slices as a goes from 0 to n, however many slices we decide to do. So that would be the Riemann sum from I equals 0 to n of, we have a formula for a sub I, 6/5 h sub I delta h, right? And we would add all those up. And then, if you remember what we did after that, is we did a very important piece. We took the limit as n went to infinity, because we said the more rectangles we have, the better our approximation. Now, here's what was great about that. When we took the limit as n went to infinity, what did that turn it into? It turned it into our definite integral. So we are going from discrete to continuous. So there's going to be two major changes. Number one, I already know the area for the ith slice. It's going to be 6/5, except I'm just going to use h, not h sub I, and dh. Just as we did back when we did Riemann sums to a definite integral. The reason I'm not using the sub I, I'm no longer in the discrete case, I'm in a continuous case. This is going to continuously add up every single infinitely small slice to get this area of this triangle. The last thing I need are my limits. And remember what our variable is, is h. The smallest h can be as up here with the way we measured it at 0, and the largest is when it's all the way down here at 10. So 0 to 10 are going to be our limits. So let's calculate that integral and see what we get. So I'm going to go down here. We can always come back up. So first off, the antiderivative here is 6/5 times h squared over 2 from 0 to 10. We can reduce this a little bit. So we have 3/5 times h squared from 0 to 10. Plugging 10 in, we'll have 3/5 times 10 squared minus 3/5 times 0 squared, which is just 0. 10 squared is 100. 3/5 times 100 is going to give us 60 square units, whatever our units are. Exact same as what we saw before. Now, again, we could have done the area of this triangle just using our old 1/2 base times height. The point of this video is to introduce you to the idea of slicing, because what we're going to see is this is going to go out and start to work on volumes, and then we're going to actually be able to do some things like center of mass and some physics with this slicing technique.